I would, is not the fun part of my job, but normally it's like part of my job. This year I'm like, yeah, okay, Dal is not making me do that so much, so I'm just not going to try, because really there's no way I can catch people. But the final is still some sort of attempt at that. You know, the final check is say, like, did you actually learn this stuff? At some point in the course, you have to have all the material in your head at once. So, speaking of which, let's keep going. So, greedy algorithms. I have to restart the timer. Greedy algorithms. So Huffman coding. Remember, I did this sneaky thing where I made you sort of rederive the proof of correctness of Huffman's algorithm by pretending that we were sorting, figuring out how to merge lists. Minimum spanning trees, and then so this was nice because we saw Kruskal's, Prims, Borovka's, and then we talked about like, okay, with Kruskal, why do you need all of these? So Borovka's, for example, you can do it in parallel. Kruskal's, it sounds super easy until you find out that you need a union-find data structure, which we hadn't learned until that point. So Prims, you need a priority queue, so it's actually, once you know how to do a super fast union-find data structure, Prims is actually a bit slower. But you have things like, okay, Prims, you always have a tree. Kruskal's, you don't always have a tree. So Prims, you're just adding things onto the tree. So like if you had road building material, road building equipment that can't go over a dirt road unless it's paving it, then you want to run Prims instead of Kruskal's. Okay, so this was this the first time that, well, we saw Van Leuven's algorithm for building a Huffman code that used that used two queues. But this was sort of the first time we saw a data structure where we really needed a sneaky, cool data structure to make our algorithms run fast. Then we did more greedy algorithms. We did activity selection, Supowitz algorithm for partitioning a sequence into the minimum number of increasing subsequences. There should be an R in there, it should be two approx, not two apox. For vertex cover, that was where you find a maximal matching and then take both ends of each edge in the matching. And that gave you, and because each edge has to be covered, at least one of the endpoints has to be in a minimum vertex cover, or in any vertex cover actually. And then you say, okay, and you can't get two of the edges in the matching with one vertex because you never share an endpoint because that's the definition of the matching. So you know that the minimum vertex cover is at least half as big as the vertex cover you get, so you get a two approximation. So this was the first maybe it was the first. It was anyway. It was an approximation algorithm. Then we saw vertex cover on trees, and we saw fractional knapsack. So fractional knapsack is when you can cut the stuff. And this was the chapter where it was like, where we did ad nauseum, before we take any steps, our empty subsolution can be extended to an optimal set, blah, 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 blah. This came up over and over again in that chapter. Okay, so that was greedy algorithms. Then, the sun is starting to shine. Then we started on dynamic programming. We didn't have a lot of chapters here, but it's an important section. And some of the chapters here were quite dense and long. So there was edit distance and also longest common subsequence. So this was where you have those, remember the black and red arrows, and you can go across. If for edit distance, you can go across the red arrows for free, and for longest increasing subsequent, and the black arrows cost you money, and then for longest increasing subsequence, the black arrows are, you don't get anything, and the red arrows you get paid for going across. And so we did alignment, which I'm sure everybody loves because that showed up on at least on an assignment, and I think also on a midterm. Yeah, so everyone should remember alignment. And then we also did local alignment, which I put on the exam I put on the exam 2 years ago. So edit distance, lots of stuff there. Subset sum and knapsack. So now we're talking about binary knapsack. So you can do these with dynamic programming, but we got into this idea of, how do you measure the complexity of the algorithm? You measure it in terms of the size of the input, that is sort of the size of the piece of paper I need to write the instance. And so if I'm writing a number, the size of the piece of paper I need to write the number is going to be logarithmic in the magnitude of the number, unless I'm writing in unary, in which case it's going to be linear. The base of the logarithm, of course, depends on the base of the number system I'm using. But that doesn't matter, but that doesn't change things by more than a constant factor, unless the base is 1, in which case it's unary, in which case things are linear. And remember, we illustrated this by saying factoring. I encouraged everyone to watch the movie Sneakers, about what happens if we figure out how to factor quickly. It's traditional for people to mess up and say factor prime numbers, which is pointless, but you actually want to say factor large numbers. But it's easy to make that slip. I have definitely done that sometimes. I'm not sure if I did that in this course. Okay. So the illustration is like, can you write a program that takes time, sort of linear O of n steps to factor a number n? It's like, yes, that's really easy. Write a for loop for I equals 1 to n. 2 to n minus 1. 1 to n, because if you include 1 and n as factors. So you get a list of all the factors. 2 to n minus 1 if you're checking if n is prime. Forget the details there. So then we did optimal binary search trees. So this was, remember you say, okay, suppose we have a subtree and we have the optimal binary search tree on keys I to j, and now we have that for all of the subtrees of size up to like s minus 1, and now we're going to try to do it for size s. So thus we filled in the diagonals. Okay, and then we did canoe speed up where we said, okay, so that was on an assignment, I think, where we did this thing like if you add stuff to the right. Okay, you don't, I'm not going to ask you about canoe speed up. But so remember how to build optimal binary search trees, longest increasing subsequences. That was another one where we needed the data structures because you need dynamic range max data structures. And why? Because so you do this thing where you have. Do people remember how to do the longest increasing subsequence with it? So if you do it naively, you have to scan for every time you look at Si, you have to scan through S1 to Si minus 1 to find you have this array that says for each of these numbers how long is the longest increasing subsequence that ends at that number. So you scan this. And for everything that is smaller than Si, you check and you choose the maximum, blah, blah. But if you have this data structure, then it becomes n log n. So, yay, data structures. So even though there were only 3 chapters, it was quite a lot of material. And then you also had the assignments with other dynamic programming problems on them, which I didn't write on the board. Maybe that's why it's not as crowded this year as it was last year. We did NP completeness, and so I should have underlined this, because even though It was only one chapter. It was a biggie. So there's reductions. The idea that I want to be able to A reduces to B, so reducing turns into... Somebody pointed out that reduces sounds like it gets smaller. But we're usually... a reduction means that the thing that you reduce to is at least as hard. So somebody was complaining that it's counterintuitive. Just think of reduces as turns into. So if A reduces to B, and we have a polytime in polytime, and we have a polytime algorithm for B, then we have a polytime algorithm for A. Right? And this means that we have an instance for A, we can turn it into an instance of B, such that the instance of A is a yes instance if and only if the instance of B is a yes instance. Okay? So we did lots of reductions, ranging from the very simple, so reducing independent set to clique and vice versa, and vertex cover to independent set, and then remember we did, I'm going to use a different color, I'm going to use blue. We did all of, so we had independent set and clique and vertex cover. Let me see. So these two are easy and these two are easy. So that means these two are easy. And then we did the reduction from 3-sat to clique. Actually, we did the reduction from 3-sat to independent set because it involved me drawing fewer lines. Usually it's, I think in the textbook it's 3-sat to clique. And we did clique to sat. And then obviously if you can do sat, you can do 3-sat because it's a special case. And then you had this wonderful Satan transform for turning for the blah blah, and then we had coloring, and we had handle path, and we had all this kind of stuff. So that was all in reductions. So we should be pretty good at reductions by now. Although, to be fair, I'm not going to ask you for a hard reduction on the exam, because everyone would fail. Almost everyone would fail. Possibly everyone. Possibly almost everyone. If I'd had to write hard reductions on my finals, I would have failed. So I mean, I could put it on as a bonus question, because it's always fun to identify, like, if somebody gets it. So I'm not going to do this year because Val would probably not approve. But when I was teaching in Finland, and in Finland you're allowed to do really hard things because I don't know. So at one point, working with my former PhD supervisor, we'd solved a problem. We'd come up with some really cool trick, and we wrote the paper at the same time I was preparing the final. So I put the open problem, I put the problem that we'd solved in the paper onto the final, I think as a bonus question, but with a big hint. And so 3 people actually got it. And then, yeah, and I think the paper got accepted. Maybe it was the final. I think, or maybe, when I was preparing the final. Anyway, I actually had the chance to tell everyone when I was announcing the marks, the paper had been accepted, and also to congratulate the people who'd figured it out. It wasn't like it was a big hint, but I was still super impressed. Because now, admittedly, it was a class of 30, so three people is actually a lot, because it was also only like a 3-hour exam. But I'm not going to do that this year. See, that's what I said. Like, you can have fun with finals. That was like lots of fun. Okay, Cook's theorem. So, sort of know Cook's theorem. I mean, you should know Cook's theorem just in general. By the time you get out of this course, you should know Cook's theorem. You should sort of know why it's true. I'm gonna promise that you don't have to know Turing machines. You don't. You should know something about Turing. I mean, remember something about Turing machines, just because otherwise if you go out and you meet somebody who's done complexity theory and stuff like that, and you don't know what a Turing machine is. So the reason to know this is because if you don't know, people will laugh at you. Maybe not openly, but for example, I remember when there's a language called Turing, which I had to learn at Queen's, because it was like a collaboration between like some prof at Queen's and some prof at U of T, I think. So it was only ever used in like some high schools in Ontario and like 2 universities, and I don't think it's used anymore because. But it was sort of like a C clone language. It had some nice stuff, but I don't remember anything about it. But yeah, it was Queen's little personal, like private language, so we had to learn it. But the key thing, it was taught at some Ontario high schools. So when I was in grad school, I was in the scuba club. And one time, for reading week, we went scuba diving. We went to an island and we scuba dived for a week, scuba dove, whatever it is. And there was this one super annoying guy on the trip who, unfortunately, so we got paired up, and we had this, so I was in the same room with him, so I was totally sick of this guy. And so one time, so somebody was asking me what I study, and I said, oh, so, computer stuff. And they asked me, like this, and I said, no, like theoretical computer stuff. So, Turing machines and stuff like that. And this guy said, oh, Turing, we learned Turing in high school. So I didn't say anything because I just didn't want to have another conversation with him. But I thought, okay, before he said that, I thought he was probably a moron. But when he said that, I was sure he was a moron. So it's important to at least sort of know what a Turing machine is, to know that a Turing machine is not something that passes the Turing test or something like that. To avoid saying things like that and have your scuba diving partner think you're an idiot, it's important to know what a Turing machine is. So Cook's theorem, you should know what it is, and you should have some idea how it's proven. Okay, more graph algorithms. Did I restart the timer? Yes, I did. Okay, more graph algorithms. You should know depth first search. No kidding. You're in 3rd year computer science. You should definitely know depth first search. In particular, you should know topological sort and strongly connected components. And I will forgive you if you aren't sure whether or not to put a hyphen there because neither am I. I have a feeling there should be, but I don't think anybody puts it there. And breadth first search, you should know breadth first search. So I was trying to show you this thing about like, in one of the years, so I was talking to some people yesterday, and they are still traumatized by I put the cabbage, the goat, and the wolf question. People usually do this in AI. They used to do this in AI classes before AI became just sort of machine learning stuff. But you have this thing of like, okay, figure out how to you're on the side of the river and you have a cabbage, a goat, and a wolf, and blah, get the three of them across the river, but you have a boat that only carries one of them. Like, how do you, and it's just a state space search. So you're doing this kind of stuff now with water jugs. So that's a BFS, and then there's Dijkstra's, and Dijkstra's is sort of a BFS, but with a priority queue instead of a queue. So you should know Dijkstra's. Oh, actually, that note to self: don't waste time on the bonus question. So when my first year in grad school, so yeah, don't usually. This is terrible exam taking strategy. But I would always go for the bonus question first because it was usually the most interesting. And I was in Cook's logic class, and I spent the whole exam the whole time trying to figure out the bonus question. And in fact, I think I got the bonus question. I got it at the end. I got it, and I think I got one other question out of 10. But I was the only one who did the bonus question, so somehow I passed. I'm not sure how that happened. Right. Okay. But yes, don't do that, because then I would have to fight Val to like be able to pass you or something like that. Now there are all these rules and regulations, so I can't just randomly assign marks. Bellman-Ford. Okay, so this is if you have negative weight edges, but you don't have negative weight cycles. Matrix, what we're calling matrix multiplication, which is actually like min plus, right? Where normally matrix multiplication, you do a sum of products. Here you're doing a min of sums. Okay. And Floyd-Warshall, where this is sort of like the matrix multiplication, except instead of multiplying it, you're saying, okay, what's the shortest you can do from here to here using only intermediate vertices up to vertex k. Okay, so this gets rid of a logarithmic factor. So here you use repeated squaring, so you get n cubed log n, and here you get n cubed. Network flows, these should be still familiar, still fresh in your mind because we saw them just last week. Remember, you write the capacities, and then you sort of choose a flow, and then you write, okay, so you have the flow over the capacity, and then you build this residual, which is, the tricky thing is you have, so the edge, the amount in either direction is, you have to, if you have a flow going this way, then you can reduce it by that much, so you put sort of an edge with that much going the other way, because you can change it. So reducing a flow from A to B is like adding a flow from B to A, blah. It's in the book. Oh yeah, so you can use the lecture notes, and remember I posted sections of the CLRS because I didn't get around to writing lecture notes for this stuff. Actually, I skipped over this. You do not have to know zero knowledge proofs, and you do not have to know fine-grained complexity. So, also because I didn't write the lecture notes for those. I didn't write the lecture notes for those, and I didn't write the lecture notes for this stuff, but I posted sections of the textbook. And network flows, and you do not have to know diagonalizations. So the halting, the countable and uncountable infinities, the halting problem, Kolmogorov complexity, fun stuff like that, except it's on assignment 8. Somebody's whistling outside my apartment. Oh, look, so that's, so we only used 2/3 of the lecture time. I must have gone much easier because last year the board was full and I used the full 90 minutes going over what everyone had to know. This is weird. It felt like a full course this year. Okay, I'm going to reset this and restart this, and then I can, I don't know, answer questions.